Hello, this is a video for moving around with some of the equations that are on the AP Physics 1 equation sheet. So what you should do is you should have your equation sheet out. So pull up either electronically or physically your equation sheet. We're going to be taking a look at these equations right in here. Oh, not that last one. These equations right in here. Okay, those three, and how to manipulate those just algebraically to get some versions of equations to help you think about different ways to attack and solve problems that deal with simple harmonic motion. So let's go ahead and do that. All right. So the first thing I want to show you here is with that first equation, okay, where you can forget the middle part. And if you forget the middle part, you just have t equals 1 over f. Now this is going to be coming up with our wave stuff as well, our waves and sound unit. But you can rearrange this, okay, and obviously say that f equals 1 over t, where t is the how long for one cycle, it's the period, and frequency is how many per second. Okay? So they're the reciprocal of each other. You just take one to the negative 1 power, you get the other one, right? Okay. So this is how often something happens per time, and it could be anything. Okay. When we're in waves and sound, it'll be the number of oscillations for a sound wave per second. For our simple harmonic motion stuff, it's how many per second, how many wave crests per second, or how many wave troughs, or how many wave lengths per second. It can be pretty much anything. It can be how many oscillations per second. So any of that stuff per second is what frequency is. It's how frequent it occurs. Okay, period is how long it takes for one complete thing. So one complete oscillation. Oh, also while I'm here talking about that, for a pendulum swinging back and forth, imagine it swinging that way, comes out, stops, and then comes back the other way. One period would be all the way out, okay, and then all the way back. Or if you're thinking about it like here versus here versus here as it's swinging back and forth, okay, if you started here, you'd have to go from here to here, back to here. That is not one oscillation, okay, because you got to do everything you're going to do. So that means you also have to come up here and then come back down. Okay, so you got to cover all of that stuff. Okay, so if you were starting at the lowest point, you'd have to go that way, come back up this way, and then come back to the lowest point. Or if you're starting here, it's out and then back. Right? So you got to account for one complete oscillation. Similar ideas for springs. Oh, by the way, when you're dealing with springs oscillating back and forth, would be like the equilibrium point for a spring. No, we are not actually in equilibrium here because our force upward is bigger than our force downward to keep us moving in a circle for a split second there. But you can think about it for energy and simple harmonic motion ideas. You can, if you prefer to think about pendulums, you can do that to help you understand springs. So for a spring oscillating back and forth, when it's at its equilibrium point, that's when it's going its fastest. Just like a pendulum, at the lowest point, it would be going its fastest. At the highest points, or farthest away from equilibrium for a spring. So imagine it's oscillating about my hand right here, or the middle of the paper. Sorry. So it would go out, come to a stop, come back, go out, come to a stop, come back, similar to a pendulum. So there's a lot in common here between these springs and pendulums. So you can think about either one that you prefer. You can switch it up if you are talking about energy ideas or the simple harmonic motion. Be careful when you start doing with forces and accelerations because then it's not exactly the same, obviously. All right. So there's that first little bit right there, okay, just regular old period and frequency. And now what about if we want to do stuff in terms of omega, our angular frequency? Okay, so now I am going to use the middle part of that equation equal to 1 over f. So we have 2 pi over omega equals 1 over f. So I'm using the right side of that equation, that first equation, okay? And now let's just cross multiply here. So we'll get 2 pi f equals omega. And this is what most people, I think, usually remember when you're dealing with omega, the angular frequency. If you want omega, the angular frequency, and you have the regular old how many per second in hertz, by the way, the units on this, 1 over a second, or a hertz, or s to the negative 1, just depends on what you're dealing with, which one of these you're likely to see. But if you've got that regular old frequency, that how many per unit time, and you want angular frequency, just multiply by 2 pi, and now you'll have the angular frequency for that. Okay, and then going back the other way, obviously, if you have omega and you want regular old frequency, divide by 2 pi. Okay. Now, the period of a spring and the period of a pendulum. This is the time it takes for one complete oscillation, which we already talked about up here for a pendulum. If you were starting here, you'd have to go that way and then back. Or if you started one of the highest points all the way out, all the way back. Okay, for a spring oscillating back and forth, if this was the equilibrium point, it would have to go out here, come back, and then keep going, come out here, stop, and then come back. Okay, and it would be moving in the middle. So, period of a spring would be 2 pi. Let's make sure I write it the same way they do. Yep, they didn't use anything special. Square root of m over k. Students, when we used to students used to refer to this as smack when we had to memorize equations, which we don't have to do anymore, thank goodness. Okay, because it's like SMK. Just remove the vowel, and also c is reserved for the speed of light, so that doesn't make any sense in the equation. And then there's that 2 pi square root thing. And then for period of a pendulum, it's 2 pi square root of L over G. And this was what students referred to as plug. Okay, you got the 2 pi, the square root, and then the L is in the numerator, G is in the denominator. Note that this equation here, this equation right here, only works for small angles. If you have large angles, don't try to apply this. Everything will fall apart. But if you're at small angles, like 10 degrees-ish or less, it doesn't matter what the mass of the object is. If you take a pendulum and you put it out like this and you let the thing swing down, okay, at this point, or even up here at this one, now the mass of the object absolutely matters, because that's affecting at the beginning here, it's entirely due to the weight of the object is the reason we're going to fall down, type of thing. So you gotta watch out for that. But for small angles, this will work. This will work. They call that there'll be a little bit more about this in AP2. Strangely, actually, in waves and optics, something called the small angle approximation. But anyway, that doesn't matter for right now for AP1. So just know that this equation works for small angles. Okay, and these two equations obviously look very similar, right? Because again, you can think about springs or pendulums when we're doing the simple harmonic motion stuff, and they can both be described in terms of their position, in terms of cosine or sine, whichever you prefer. But then sometimes you don't want this. Like you might want this. You might want frequency in terms of m and k, or maybe you want angular frequency in terms of m and k. These are the ones that people typically remember, but then it's just some algebra to figure out those other ones. Okay, so let's do this and figure out what it would be in terms of frequency. So if we wanted frequency, what would the frequency of our oscillation be instead of how long for one? Remember that they're just the inverse of each other, right? So I can just take this equation to the -1 power and end up with my equation for frequency. So let's do the square root first part. That basically means flip everything. So k over m. And then, of course, I'm going to have a 1 over 2 pi out front. So just flip everything around. There's our frequency for a spring, frequency of a pendulum. And this can help depending on the type of question you're asked. This might be an easier way to think about it. You can obviously do this and then do 1 over it if you want as well. So this one, flip again, G over L, and then the 1 over 2 pi. So there's a couple useful things that you could do on the problems. And then what about in terms of omega? What if you want this in terms of for omega? So what would the angular frequency be of a spring? Well, to get omega, we would just take our regular frequency and multiply by 2 pi. So by 2 pi, because it'll cancel out. So it'll just be square root of k over m. And then omega of a pendulum, square root of g over, that's square root of the whole thing. Square root of g over L. I'll rewrite that. Square root of g over L. Okay, so that's just, again, we took our regular frequency and multiplied by 2 pi to get this. So all of those could come in handy, and it's just a little bit of algebra to move around between them. All right, last thing here, got a little bit of room down here, is I did want to briefly mention that we have x equals a cosine 2 pi ft. This is on a slightly different spot on your equation sheet. It's over by the motion equations for rotation and above the torque equals I alpha equation. And then you notice this 2 pi f in here, that 2 pi f. Well, remember, omega is 2 pi f. So you may have heard me at some point in a video or at some point in class again, you might hear me say like a cosine omega t or a sine omega t. That's what I'm doing. I've just done that substitution in my head. I didn't say the whole 2 pi f thing. I just replaced 2 pi f, replace 2 pi f with omega. So you can do that as well. Also, if you have calculus knowledge, it's fine if you want to think about velocity as the derivative of this, and then switch from cosine to sine, throw the negative on there, that kind of thing. That's perfectly fine. You don't need any calculus to solve any of these problems, and there will be a special case that we'll talk about. I'm going to add that to my list of things to do here. At some point, there will be a special case on where you're not allowed to use calculus, and I will make sure you know that before you take your AP1 final. There's only one spot where that comes in, but obviously, even if you're not allowed to use calculus to help explain an answer, the calculus could allow you to quickly arrive at the answer, and then you could work out the conceptual part from there. But there is this one spot in AP1 where they do not allow you to use calculus to answer a question. It's very strange, but that's what they want. And I'll let you guys know about that. If you have any questions on this stuff, or how to move around, or the algebra involved in it, let me know. Also, if there's other equations on your equation sheet from the new ones or old ones that you're not sure on where they're used, or how to apply them to problems, you can ask about that as well. A reminder, office hours are 9 to 10 a.m. Monday, Tuesday, Thursday, Friday. Thanks, guys. Have a good one.